let's evaluate this integral. The first thing to notice is that the degree of the numerator is greater than or equal to the degree of the denominator. This fact tells us that our first step is going to be polynomial long division. We can set up that division problem like this. Notice that I'm putting zeros in for placeholders just so that I don't lose any terms. And the first question we ask is, what would we multiply by x squared to get x cubed? The answer is x. We can then multiply that x through this polynomial here. After doing that and writing it down here, what we do is subtract. X cubed minus x cubed is 0. That was the idea. 0x squared minus 4x squared is negative 4x squared. And 0x minus 3x is negative 3x. We can then bring down the next term. The next question we want to ask is then, what would we multiply x squared by to get negative 4x squared? The answer is negative 4. Again, we can take that negative 4 and multiply it through this polynomial. Having done that, we can subtract again. The negative 4x squareds cancel. Negative 3x minus a negative 16x gives us a positive 13x. And 35 minus negative 12 gives us a positive 47. Now, what we've done is we've rewritten this integral as the integral of the quotient x minus 4 plus the remainder, which was 13x plus 47, divided by the original denominator, x squared plus 4x plus 3. And the question now is, can we integrate that? Well, for these first two terms, the answer is yes. But for this last term here, right now the answer is no, but we can integrate this if we do partial fractions. So I'm going to make some room for some partial fractions. The goal is to rewrite the last term in a form that we can integrate. And the first step in doing that is factoring the denominator. And now, because the degree of our numerator is smaller than the degree of our denominator, partial fraction says that we can split this up into these two terms. Because both of these factors are linear factors, both of the numerators can just be constants. If we want to solve for those constants, what we need to do is multiply every single term by x plus 3 and x plus 1. We do that because that cancels all of the denominators on both sides of the equation. And after making all of those calculations, we are left with, and while there are multiple ways to solve for a and b here, probably the most straightforward way to do it with this problem is to choose a couple of values for x and plug those into this equation to solve for a and b. You'll notice that choosing x equals negative 1 will zero out the a term on the right side of this equation, leaving us with 34 equals 2 times b, which pretty quickly gives us b equals 17. If we choose x equals negative 3, that will zero out our b term on the right hand side, leaving us with 12 equals negative 2a, and we can get a equals negative 6 out of that. Now, we did all of that partial fraction work just so we could rewrite this integral one more time. Because now, instead of this term in our integrand, we're going to be using this term, using a equals negative 6 and b equals 17. And that looks like this. This leaves us something that we can integrate pretty quickly. The integral of x is 1/2 x squared. The integral of 4 is 4x. The integral of this third term is going to be negative 6 times the natural log of x plus 3. And the integral of the last term is going to be 17 times the natural log of x plus 1. Don't forget your plus c. And that answer looks excellent to me. So I'm going to zoom out on some of that work and see how much we can get onto one page. Oh, it looks like we can get all of it in there. So I'll let you take a look at all that so you can see all of the nice work that we did. Okay, thanks for watching. I hope that video helped. And if it did, I hope that you'll watch the next one as well. I'll see you there.